this is a work related to time-dependent problems, and specifically periodically time-dependent problems. So, you know, if you come from condensed matter, you can think of it maybe as some material on which you are shining very strong light. You're probably familiar with such experiments. I'll review them in a moment. So, and we try to describe an effect that is known as prethermalization. So I'm going to define what prethermalization means. Okay, let me start by thanking the group, and in particular here for this work, more. So you can't see him in Zoom, but you can see a picture of him here. And Jonathan is also here in the picture. So these are More and Jonathan who are here. So hi, More and Jonathan. And it's also a collaboration with a previous postdoc of mine and 2 colleagues. Okay, good. So as I mentioned, periodically driven systems are very interesting. And we know by now some experiments that have highlighted why periodically driven systems can give rise to new physics. One example are these waveguides, in which, so the waveguide has a structure, it's like a spiral, and so the spiral basically mimics a periodically driven system. And what's happening here is that by engineering the shape of the waveguide, which basically is like engineering some type of periodic drive, you can lead the system to interesting phases, like topological phases with some interesting edge effects. So situations in which if the light enters in the middle, it will sort of go all around. But if you start it in the edge, it will stay. So if you start it, say, from a waveguide that is on the edge of this system, it will stay on the edge. Probably go around, but still it will not diffuse in the waveguides that are in the middle. Okay. There are also experiments with materials, like this experiment, in which one can, again, one applies a very strong pulse and basically excites higher Floquet bands. Usually these are pump probe experiments. So these are experiments that are done on a very short time scale, in which you pump the system and then right away you come and probe it. The reason is that condensed matter systems, they relax to equilibrium very fast. So you need to really probe short time dynamics. And this is another example done with some synthetic materials, and in which one can give the periodic drive can give rise to what is known as a time crystal. So a time crystal is a state that breaks the periodicity of the drive. So the drive is periodic with every single period, right? After every period you have the drive comes back to its own, but in a time crystal, the system breaks that symmetry. So the system oscillates at a frequency that is lower than the frequency on the drive. Okay, good. So let me give you an example. This is a beautiful, the physics demonstration that explains this idea, in which you start from a saddle. So you have a saddle, and clearly the saddle is not sufficient to trap a ball. The ball will always fall in one direction. And now we are going to use a periodic drive. So we are now going to use the periodic drive to actually create a trap. So what is going to happen is that the experimentalist is now going to to start rotating. You see, you now start rotating trap. And when you rotate the trap, actually, you can create a trap that works on the on both directions. So you see now the ball is trapped in both directions. And this is thanks to the periodic drive. Actually, this is really used to trap ions. So as you probably remember, you cannot trap ions by just applying electric fields, static electric fields. There is even such a theorem. In vacuum, you cannot do it, because there will always be. So what you can create a sort of a saddle point, but not really a local minimum. There is always a way for the ion to escape. But when you rotate it fast enough, then you can create a trap, and this is working principle of the pole trap. Okay. So now, what is the problem? So the problem is heating, meaning that what happens is that because you are applying a drive, the system will absorb energy, And now in condensed matter, what happens is that there are the phonons. So the phonons eventually dissipate all the energy and actually eventually bring you back to equilibrium. But in a system like a synthetic system that does not have phonons, so there is no buff, it's an isolated system, and you pump it, you always pump it more and more, and the energy just increases as a function of time. So eventually what will happen is that you will reach an infinite temperature ensemble where the system thermalizes to an infinite temperature ensemble, just because it's absorbing more and more energy. And okay, good. So what will happen eventually? That you end up with some thermal state. So here HF denotes the Floquet Hamiltonian. So the Floquet Hamiltonian is the Hamiltonian that describes the effectively describes the time periodic Hamiltonian. So this is the interesting physics. The interesting physics, the new physics comes in the Floquet Hamiltonian. Say the time crystal or whatever interesting physics you have, it's a property of this Floquet Hamiltonian, which is the Hamiltonian that is engineered by the periodic pump. However, if you wait very long times and the temperature is infinite, you see that the distribution function is 1 over the temperatures times the Floquet Hamiltonian. So maybe the Floquet Hamiltonian is really interesting, is topological, is whatever you want. But if the temperature is 0, well, then you end up in a trivial distribution, just in a trivial state, right? Just this infinite temperature state. So whatever you have done, you have a very interesting dynamics, but eventually the thermodynamics, the probabilities are just a constant. So it's very boring. Okay, so that's bad. So the question is really how to limit the heating of a system. And this can be done in several ways. So one, if you have an integrable system. So actually, that one is if you have just a small system. So you know that small system, they cannot absorb energy forever, right? They are small, they have just a small number of states. They do not absorb energy. That's method one. And this is related to integrability. You know that if you have an integrable system, effectively you can divide it into degrees of freedom that are decoupled to each other. So each degree of freedom is like a small independent degree of freedom. Another way to do that is to use disorder. And with disorder, you can localize the system. And again, a localized system, you can think of it as an emergent integrability. So again, you have localized particles that are like small subsystems that do not talk to each other. That's basically the idea of localization. Here we want to describe another pathway. So this is a way that works generically. So you have a generical, non-integrable model and you drive it. But here the idea is to drive it at very large driving frequencies. So you drive it very, very, very fast. And what happens? What happens is that think of a system that has a typical energy scale. So that's the typical energy scale of each degree of freedom. And you are pumping it very, very fast. So when you pump it very fast, it means that in order to absorb some energy from the drive, you need to absorb a photon of the drive, right? It's quantum mechanics. So there is a quantum of energy, and that quantum of energy is very large because the driving frequency is large. So if you want, this would be h bar omega. It is very large compared to the typical energy scale of the system. And so if you want to do that, if you want to absorb that big chunk of energy, you need to take many, many, many small perturbations. You need to perturb many, many, many local degrees of freedom. And this is equivalent to going into very high order in perturbation theory. So you need to, if you have a small parameter epsilon, you need to go to the epsilon to some power that is large, because the ratio between the driving frequency and the small bandwidth is large. So, and this is clearly an exponent. It's epsilon is smaller than 1. This is an exponential suppression. So that means that if you drive the system fast, then it will absorb energy slowly. Our energy absorption is very small, and then maybe you can do interesting stuff before you reach the infinite temperature ensemble. So the energy absorption is small. And actually, this is one can make it a rigorous theorem for quantum system, like spin system, in which each degree of freedom has some energy, and again, you are trying to absorb a huge chunk of energy by very small bites. Okay, good. So now, where can you observe it? So, let's ask about experiments. So one possibility is to look at, say, the Bose-Hubbard model. So systems of ultracold atoms in which this is just a standard description of of a lattice in which you have atoms, so the atoms can hop from one lattice to the other. And you can, for instance, periodically modulate the hopping term. That could be one way to proceed. So this experiment was indeed performed last year or this year. And what you can see here are the results. So what you see on the y-axis is the heating rate. So large heating rate is you absorb a lot of energy, and small heating rate is you absorb very little. So let's say up is bad and low is down, is good. And what you see here on the x-axis is the driving frequency. And then as you can see, so forget for the moment for the colors, let's just focus on the dark blue. And in the dark blue curve, what you see is that when you increase the driving frequency, the heating rate goes down very, very fast. Actually, this is the numerical simulation of the experiment. It's sort of the experiment resembles this. Okay, you know, an experiment is very hard to measure 10 to the minus 20. So this is just numerics, but if you look into the paper, you will see that there is a fair agreement between experiment and theory. Okay, so what is the highlight? The highlight here is that there is here a slope. So because this is a logarithm and this is a linear scale, a linear curve here means that there is an exponential dependence. So the heating rate sorry, goes like the exponent of minus the driving frequency. So there is an exponential suppression of heating. That's the key observation, and it's seemingly it goes along the lines that I was telling you before. You know, remember this big chunk and the small bites that you are trying to eat. The problem is that this is not a spin system. This is actually a particle system. So you have particles, and each particle can absorb any amount of energy. You see that the energy per particle is not bounded, right? You can put as many particles as you wish on a single site, and then the energy per particle is unbounded. So it's a little bit like a particle. It's like this term resembles like the kinetic energy. You can think of it as the kinetic energy, and the kinetic energy can grow indefinitely per spin. So for spin system, you can have up to some amount of energy per system. The energy density is bounded. You can have only a limited amount of energy per particle, and that's where all these theorems apply. But in this case, you can have any infinite number of energy per site. So in this case, you cannot apply all those theorems. And then you can ask yourself, well, it turns out that there is an exponential suppression even if the theorem do not apply. So these theorems do not apply. There is no bound. There is no rigorous bound on the absorption, but still the absorption is exponentially suppressed. And you can ask why. So here I would like to propose an approach that is based on a semi-classical approximation. So the idea really is just to move to semi-classical degrees of freedom when the number and the phase are canonically conjugate. So, you know, this is the usual b goes to e to the I phi. I hope both Gianluigi and Daniel are familiar with that. And so what you get here this cosine term that is just the pi bj becomes a cosine term. Okay, so this is semi-classical approximation, and what you get is a non-integrable classical or semi-classical problem, and you need to ask, how can I show that there is an exponential suppression of heating in this model? So I'm going to show you here two arguments. One is based on some our older work. Actually, this is not really sufficient for the exponential suppression, and then I'll briefly mention these new works in which we do see an exponential suppression and try to link it to the experiment. Okay, good. So the first method is just based on a quadratic expansion. So you take your cosine and expand it quadratically. So you get just a set of harmonic oscillators. And you know that for, okay, again, you go to Q space. So these are just a set of harmonic oscillators in Q space. So for each Q mode, you have a frequency. Like, okay, this is just the dispersion relation of the medium. And then there is, so you see that there is a bandwidth. So this is a many-body bandwidth. So this is not the bandwidth, this is not the bandwidth per particle, this is not the bandwidth per site, but this is the bandwidth per bosonic mode. So of course you can put as many bosonic modes you want, but each mode will have a given frequency. So the energy is unbounded, but in a quadratic model, what you have is that you have just independent bosons, and each boson, for each Q mode, there is a typical energy. So there is a Q, omega of Q energy. And so what you get from here is that now the driving frequency, now you need to ask yourself, what is the driving frequency with respect to the bandwidth? So if the driving frequency is smaller than the bandwidth, then you can excite it. So you have technically it's called the parametric instability. It means that your drive can excite such a boson, and then there is energy absorption. While if you are a driving frequency above that bandwidth, then there is no energy absorption. And this is what you get. So this is basically explains you this transition between high energy absorption on the left and low energy absorption on the right. So in the quadratic model, what you would expect is just a step to have a finite value of energy absorption on the left and zero absorption on the right. That's what you get from a quadratic model. So it's sort of nice, but it's too rough, right? It tells you that there is yes energy on the left, finite on the left and zero on the right. So this is not what you would like to explain. What you would like to explain is this exponential suppression here on the right. So you need to go beyond that. Let's look again at our semi-classical model. Okay, so this is just the model I was bringing before. These are the kicks. So instead of, this is just for numerical purpose, it's easier. Instead of having a cosine term in terms of the time, it's easier to have kicks. And then you have a non-integrable model. And actually this model had been studied before. And what people found is that this model is diffusive. So you see, these are all works by, well-known people in the many-body chaotic classical systems. And what you see, this is the time, this is time, and this is the kinetic energy. And you see that the kinetic energy grows linearly with time. So this is just basically regular diffusion. Technically, it's called the fast Arnold diffusion because the slope is small. So maybe you can see here that the slope is small, but still it's diffusion. It's just maybe not the simplest type of diffusion, but it is still diffusion. You can see that there is a linear dependence of the energy on the time. So that's not what we are looking for. But now, actually, there is something interesting. If you see that the time here, look, it starts actually 10 to the 5. So they're showing you some plots, but the time scale here starts at 10 to the 5. So what actually we asked ourselves was, okay, what actually happens before that time? What happens if at shorter times? So we have basically repeated those calculations, and this is shown here for shorter times. And now you see that it is true that at long times you have a diffusive regime, but at short times there is a prethermal regime. So a prethermal regime is a regime in which the energy absorption is low. So the energy is basically constant. Okay, you can say that there is a diffusive regime on the left, but there is a prethermal regime on the, there is a diffusive regime on the right, but there is a prethermal regime on the left. And this is what is shown here in this plot. Okay, very good. So I would claim that this is the first evidence of prethermalization in classical systems. There is also related work by Anatoly and Marin, etc. So there are some works that show that, yes, at long times, these classical systems are boring diffusive regime, boring diffusive systems, but at short times, there is new physics. And the new physics is a physics of prethermalization. So it's a physics in which the energy absorption is exponentially suppressed, and hence, you can see here, the energy is almost constant as a function of time. Okay, good. So how do we explain this regime? So in order to explain this regime, we have invoked ideas from classical many-body systems, and it's basically the idea of a resonance. The resonance is basically, you can think of it as it's the same as just the quantum resonance, right? When you have that the energy difference between two states equals to h bar omega, except that you don't need h bar. I mean, you can just really add this p, it's the angular momentum of the rotor. So it's telling you how much the rotor rotates as a function of time. This is just the angular velocity of the rotor, and you can compare the angular velocity of the rotor, pi and pi plus 1, with the drive. So omega is the pump. So it's telling you how much the drive is rotating. Pi and pj are dynamical variables. They're just telling you, look at the rotor. You see the rotor oscillates fast or slow. And if you want to absorb energy from the pump, you need to hit this resonance. You need that basically the angular difference, what matter here, the angular velocity difference between two rotors. And this angular velocity difference needs to be equal to the driving frequency. Okay, that's the resonance. Again, it's common from quantum. It would correspond to the absorption of a quantum photon, except that there is no h bar here. You really compare two frequencies. Okay, so now we need to evaluate this absorption. So we can write the resonance, but then the question is how probable this resonance is. And here what we use is the idea that the prethermal state is really a thermal state. And it's a thermal state in which what matters is the Floquet Hamiltonian. So basically the time average Hamiltonian in this case, because we are at fast frequencies. So we can use the Boltzmann distribution of the prethermal state in order to evaluate how much energy is absorbed. And in this case, what we find is that this is exponentially suppressed. So let me explain what I'm telling you. I'm asking the following question. What is the probability of finding a rotor that rotates very, very fast? Why fast? Because the drive is fast. So I look at a given rotor and I ask, what is the probability of finding that rotor to oscillate fast? And this is given by the Boltzmann distribution. So what you understand is that if the temperature is low, okay, then the probability to find the rotor that oscillates very, 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 very fast will be very, very small, exponentially suppressed. So the mechanism that we are proposing here is a mechanism based on the temperature of the prethermal state. So if the temperature of the prethermal state is small, then the rotors oscillate slowly. It's very hard to find the rotor that oscillates very, very fast. Hence, the energy absorption is suppressed. Hence, the temperature doesn't change because no energy is absorbed. And then it's sort of you see, there is a feedback argument. There is a self-consistent argument where you say, let's assume that the temperature is small. Then I see that the energy is not absorbed. And then I understand that the temperature keeps being slow. So then eventually it's really a question of the initial conditions. If you start in initial condition where the temperature is small, you will stay there for very long time. Again, there is a finite probability of absorbing some energy. So eventually you will escape this regime. Okay. So this is, I mean, it's a nice mechanism. It's quite generic. The problem is that it doesn't seem to work with the experiment. So let me show you again the same curve as before. This is the blue curve. The blue curve is the same as before. Again, it's the energy absorption rate on the y-axis and the frequency on the x-axis. And again, you see this line, which is this exponential suppression. But these curves refer to different temperatures. So different initial temperatures. Again, it's numerics, but the experiment seems to go in this same direction. What you see here is that the slope does not depend on the temperature. So in my argument, the temperature was important. I told you if the temperature is high, then there is no exponential suppression. This is in contrast to the numerics, because in the numerics, what you see is that the energy absorption is exponential suppressed even as a function of temperature. So in other words, my prediction was that the temperature should come in the exponent. So my prediction was that the slope should depend on the temperature. And when you decrease the temperature, I expected to have a smaller slope. In contrast, here you see that the slope basically does not depend on temperature. Okay, the curve goes down. That's expected because if you say are at infinite temperature, there's no energy absorption. So the fact that the curve goes down, it's okay. But the problem is the slope. And the slope here you see does not depend on the temperature. So naively, one would say, oh, if the slope does not depend on the temperature, it means that it's a quantum effect. At least this is what you see in the literature. But I think this argument should be really wrong, because if something does not depend on the temperature, it means that it survives until infinite temperature. And if something survives at infinite temperature, I would argue it's actually really not quantum. So what's going on here? On the one hand, we see something that looks like a quantum effect. And on the other, so the temperature doesn't seem to play a role on one hand. On the other, the effect survives at infinite temperature. So the answer that we found is that one really needs to take into account additional conserved quantities. So the Boltzmann weight that I constructed before, I said the prethermal state is a thermal state. I wrote e to the minus beta h, right? That's the Gibbs distribution of a system. However, this system has more conserved quantities. And as you remember, when you build the Gibbs distribution, you need to take into account all your conserved quantities. In this case, it's a system of particles hopping on the lattice. And when particles hop on the lattice, the total number of particles is conserved. So the correct Gibbs distribution is not only e to the minus beta h, this would be this term, you also need to take into account the total conserved quantities. And here, so I need to add this minus mu n minus beta mu n, right? You need to add a Lagrange multiplier that ensures that you have the correct number of particles, because the correct number of particles is determined by the initial conditions. In this case, we had, in the experiment at least, they had one particle per side. So you need to fix mu such that the number of particles is fixed. And now see what happens. When I increase the temperature, the first term goes to 0, right? I increase the temperature, this term goes to 0. The second term, in contrast, changes, because when I change the temperature, also the chemical potential changes. And eventually, because I know that it's fixed, I know that the number of particles is fixed, I need really to fit mu and t together. So when t increases, mu should increase as well. And this allows us really to, so even although the temperature increases, mu increases, and eventually you can still find an exponential suppressed excitation. So eventually it was, what we really need to do is to solve a very nice problem in statistical mechanics. I don't want to bore you with all the details. Just let me tell you what are the ingredients that we put in. So first of all, we compute the energy between the different states. So the states, you know, when you have n particle on one side and m particle on the other side, we compute the energies. Then we use this argument of resonances. So the probabilities of a given resonance. So we look for a resonance and we ask, what is the probability of finding the resonance? Again, when the probabilities are drawn from some Boltzmann weights with the given chemical potential. And now you have something like these sums that you find in the Bose-Einstein condensation arguments. So you basically need to sum over all possible number of particles. So there is a probability of having a particle, and you need to just to sum the probabilities. So it's a very nice exercise in statistical mechanics. I mean, it's analogous to the argument that was used by Bose to show Bose-Einstein condensation. But here we don't have Bose-Einstein condensation. What we are really trying to compute is the heating rate. Okay, good. So let me go to the results. So the results are following. So first of all, we can perform that calculation that I was showing you, and we end up with some expression for the heating rate. And what you see that the most important part is this exponent. You see that the temperature does not enter into the exponent. So a little bit like the plot that I was showing you before, the temperature enters in the prefactor. So it goes down with the heating rate goes down with the temperature, but the exponent is unaffected by the temperature. And again, this is true in the high temperature limit. So in principle, the temperature enters, but there is a well-defined high temperature limit in which the temperature doesn't enter anymore. And also I would like to claim that this expression really matches nicely with the numerics. So we have performed again the numerics that have been shown in the paper by Manuel Bloch group. And what you show here, so here I'm showing in this plot the continuous lines are the numerics done on a small, on a system with a small number of particles. And the dashed lines are the semiclassical approximation. So this is the black curve here is the high temperature expansion, and the dashed lines are the semiclassical approximation that I can do analytically at any temperature. For at high temperatures, like you show here, the black, these red and black are the high temperatures limit. So in the high temperature limit, I really have a closed expression. This is what is shown here. And for finite temperatures, I can do some, I need to solve some self-consistent numerical equation. It's a very simple calculation, not heavy numerics, just some solving some closed expression. But there is no analytic expression for it. And I would like to claim that the agreement is very good, especially at the high temperatures. At small temperatures, you see that it's not working as well. But this is expected because, again, it's a semi-classical approximation. So you really don't expect it to work at low temperatures. So the fact that low temperatures, you see this blue, in the blue case, the agreement is not very good. That's not surprising. What is important is that there is a good agreement with the yellow and red. Now you may say, oh, well, also the agreement in the red and yellow, which is the high temperature, is not great because look here, for at high driving frequency, you see that there is no good agreement. But actually, this is not a problem of the approximation; it's a problem of the numerics, because the numerics is done with a finite number of particles. So let me show you what happens when you increase the number of particles. So this is a lattice of free particles on free sides. This is so the analytics is always the same. The dashed curves are always the same and changing the lines. The lines refer to more and more particles. And when you see is that when you add more and more particles, it becomes 7 particles, 8 particles, 9 particles. It becomes closer and closer to the analytical expression. The reason I could not go to larger number of particles is that, as you all know, quantum simulations grow exponentially. So the Hilbert space is exponentially large in the number of particles. So already 9 particles is you need to diagonalize very big matrices, and for 10 particles you would really need a supercomputer. But anyway, the trend is clear. So the semi-classical approximation really allows us to compute something in the thermodynamic limit. Again, limited for high temperatures. This blue, this yellow and red, you see that the green is only qualitatively correct, and the blue is really out of the game. So at low temperatures, you cannot use semi-classical approximation to simulate low temperature many-body quantum system. I mean, I think it would be very bad for us if this was the case. But at least in the high temperature regime, there is a well-controlled expansion. Okay, let me skip this part. So this part is telling you that actually we can now develop not only a way to we can not only evaluate what is the energy absorption in the prethermal state, but we can really develop a method that describes the transition from the prethermal regime towards the diffusive regime. So the numerics I was showing you here is basically in the prethermal regime. So in the initial, what happens at the initial short times. Here we actually develop a method that can allow us to go from the prethermal regime to the diffusive. So really connect those two regimes. This is something that we are currently working on, and it seems to work very nicely. So we have a way to collapse all the numerical data in one into the other. But so this is still work in progress. So let me summarize. What I told you is that if you take a classical system and periodically drive it as a function of time, there is the possibility of creating a prethermal state. I mean, there are situations in which the system is not diffusive. It does not absorb a lot of energy as a function of time. It absorbs very little energy. And how much little, it depends on the initial conditions. And in particular, depends on the initial temperature. And this is sort of the generic mechanism. So the lifetime of the prethermal state is exponentially suppressed in the frequency over the temperature, the initial temperature. So the lower the initial temperature is, the more the system can be trapped in this prethermal regime. Eventually, it will escape and it will go into the regular diffusion. But there is an exponentially long times in which you can do intrinsic physics. Remember that our goal was to prevent heating. And now I'm telling you that you can actually prevent heating for exponentially long times. So this is important. You all know that exponentially growing curves are okay. Well, so what I also told you and this was really the topic of this talk, is that if you have systems in which you have other conserved quantities, like not only the energy is conserved, but also the number of particles is conserved, you need to plug that, you need to take that into account. So the prethermal state needs to take into account the possible conserved quantities that you have in the system. And by taking that into account, we were able to provide a semi-classical description of recent experiments with ultracold atoms. Okay, so thank you so much for your, thank you for listening.